There's something out there in the dark, something so strange, so utterly baffling, that even the brightest minds in science can't fully explain it. Deep in the void of space, black holes aren't just swallowing light and matter, they're sending out signals. Not just any signals, but eerie, unpredictable bursts of energy that defy everything we thought we knew about these cosmic monsters. Imagine a whisper in the silence of the universe, a message without a language, a pattern that flickers just long enough to leave us utterly mystified. Scientists have detected 25 of these unexplained signals, and each one is a riddle wrapped in the enigma of a black hole's shadow. Black holes are, by their very nature, the ultimate paradoxes of the cosmos. They're regions where gravity is so intense that nothing, not even light, can escape their pull. And yet, somehow, they're not entirely silent. Every so often, they emit bursts of energy radio waves, X-rays, strange distortions in space-time that echo across the universe like cosmic alarm bells. But here's the thing, we don't know why. These signals don't fit the models, they don't match the predictions. They're anomalies, glitches in the fabric of reality that suggest black holes are hiding secrets far stranger than we ever imagined. So what are these signals trying to tell us? Could they be the echoes of matter being torn apart at the edge of oblivion? Or are they something else entirely, something we haven't even begun to comprehend? That's the journey we're about to take. In this video, we'll explore all 25 of these unexplained transmissions, diving into the theories, the mysteries, and the mind-bending possibilities behind each one. By the time we're done, you might just see black holes and the universe itself in a whole new light. Buckle up, the unknown is calling. The first signal on our list isn't just mysterious, it's legendary. The WOW signal, detected on August 15, 1977 by Ohio State University's Big Ear radio telescope, remains one of the most tantalizing cosmic enigmas of all time. For 72 unforgettable seconds, a burst of radio waves blazed across the sky, so powerful and precise that astronomer Jerry Amon circled it on the printout and scribbled, "Wow," in the margin, giving the signal its iconic name. What made it extraordinary wasn't just its strength or clarity, but the fact that it fit exactly the profile scientists expected from an artificial extraterrestrial transmission. And then, just as suddenly as it appeared, it vanished. Decades of searching have never found a repeat, but here's where things get even stranger. Recent studies suggest the WOW signal might not have come from a distant civilization at all, but from something far more ominous. Some astrophysicists now argue the signal's peculiar frequency and abrupt disappearance align eerily with the behavior of intermediate mass black holes. These cosmic middleweights, lurking unseen in the gaps between stars, could produce bursts of energy as they rip apart wandering objects like rogue planets or dense nebulae. The math shows that the signal's intensity and duration match theoretical models of tidal disruption, moments when a black hole's gravity shreds matter into glowing, radio-emitting debris. Yet even this explanation leaves gaping holes. Why was the signal so narrowly focused in frequency, like a laser beam from the void? Why has nothing like it been detected since? And most haunting of all, if a black hole did create it, what exactly was it destroying that night? A wandering world, a cloud of exotic particles, or something we haven't even considered? The WOW signal refuses to surrender its secrets, standing as a ghostly reminder that even our boldest theories might barely scratch the surface of what black holes are truly capable of. While the WOW signal taunts us with its fleeting mystery, the cosmos has another enigma up its sleeve, one so powerful it rewrote our understanding of cosmic radio bursts entirely. Enter the Lorimer Burst, a millisecond-long explosion of radio waves so intense it outshone entire galaxies for a heartbeat. Detected in 2007 by astronomer Duncan Lorimer while sifting through old pulsar survey data, this flash was unlike anything seen before. It came from billions of light years away, packing more energy in its brief existence than our Sun emits in 30,000 years. What makes the Lorimer Burst truly unsettling is how it defies explanation. Most cosmic radio signals have predictable origins, colliding neutron stars, dying stars, or the steady pulse of spinning pulsars, but this, no afterglow. No trace, just a single, violent scream of energy that vanished without a trace. Some theorists now suspect black holes might be the culprits, specifically the chaotic mergers of supermassive ones. When two of these monsters collide, simulations show they could warp spacetime so violently that they launch shock waves of radio energy across the universe, brief, blinding flashes that match the Lorimer Burst's profile exactly. Yet there's a twist. These bursts have a bizarre property called scattering, where longer radio wavelengths arrive slightly later than shorter ones, like an echo stretched across time. Normally, this suggests the signal traveled through dense plasma, but the Lorimer Burst scattering is off the charts. Some researchers argue only a black hole's extreme environment could distort radio waves this way, perhaps near the accretion disk where superheated matter swirls at nearly light speed. Others propose even wilder ideas. Could these bursts be the death cries of stars being spaghettified by intermediate mass black holes we've yet to detect? The plot thickens with recent discoveries. Dozens of similar bursts, now called fast radio bursts or FRBs, have been detected since, some even repeating. But the original Lorimer Burst remains in a class of its own. Its energy, its loneliness, its sheer abruptness still taunt astronomers. If black holes are responsible, why don't we see more of these bursts near known ones? And if not, what cosmic phenomenon can unleash such raw power without leaving a single clue behind? The Lorimer Burst isn't just a mystery, it's a beacon shining from the darkest corners of the universe, daring us to follow its trail into the unknown. If the Lorimer Burst was a cosmic one-hit wonder, then FRB 121102 is the universe's greatest encore. This isn't just another fast radio burst, it's the first one ever found to repeat, flashing over and over from a tiny galaxy 3 billion light-years away. Discovered in 2012 at Puerto Rico's Arecibo Observatory, this signal shattered the assumption that all FRBs were one-time cataclysms. Instead, it pulses unpredictably, sometimes quiet for months, then erupting in clusters of rapid-fire bursts. But what makes 121102 truly bizarre is its home. A dwarf galaxy crammed with star-forming gas, the kind of turbulent environment where supermassive black holes often lurk at the center. The leading theory, a young, highly magnetized neutron star called a magnetar, possibly orbiting a black hole. Magnetars are stellar corpses with magnetic fields so strong they could strip the iron from your blood from halfway across the solar system. In this scenario, the black hole's tidal forces might intermittently crack the magnetar's crust, releasing apocalyptic flares of radio energy as cosmic screams. But here's the catch: 121102's bursts show Faraday rotation, a twisting of radio waves that suggests they've traveled through an insanely powerful magnetic field. We're talking conditions so extreme they'd make the inside of an MRI machine feel like a breezy afternoon. Only two things in nature create fields that strong: magnetars themselves or the chaotic plasma maelstrom around an active supermassive black hole. Yet even this explanation feels incomplete. Why do the bursts sometimes arrive in precise, hour-long windows? Why does their polarization dance in ways that defy standard models? Some researchers speculate the signal might be amplified by a black hole's gravitational lens, warping spacetime like a funhouse mirror to create eerie repetitions. Others propose an even wilder idea. What if we're seeing echoes from a collision between a magnetar and an accretion disk, sending shockwaves through the black hole's swirling debris? Every new observation deepens the puzzle, like in 2019, when astronomers caught the source emitting bursts at higher frequencies than any FRB ever recorded, as if something had violently revved up the engine behind it. What's clear is this: 121102 isn't just repeating, it's evolving. With every flicker, it whispers tantalizing hints about the brutal physics near black holes, where gravity, magnetism, and raw energy twist the laws of nature into knots. Whether it's a magnetar in agony, a black hole's gravitational fireworks, or something beyond our current science, one truth remains: this tiny galaxy holds a cosmic beacon that refuses to be ignored. And as we listen, it keeps rewriting the rules. The BLC-1 signal wasn't just another blip in the cosmic static. It was the moment we thought we might have heard our interstellar neighbors knocking. Detected in 2020 by the Parkes Radio Telescope in Australia, this tantalizing signal seemed to originate from Proxima Centauri, the closest star system to our Sun. What set it apart was its narrow bandwidth, a hallmark of artificial transmission, pulsing at 982 MHz, a frequency suspiciously free of natural cosmic noise. For a brief, electrifying moment, the world held its breath. Was this finally proof of extraterrestrial intelligence? But the real twist came when astronomers began digging deeper. Proxima Centauri isn't just any star. It's a red dwarf orbited by at least 2 planets, one of which sits in the habitable zone. And lurking in the data was an even more provocative detail. The signal's frequency drifted slightly, a behavior often seen in signals affected by intense gravitational fields. Could a black hole be warping this transmission? Some theorists floated the idea of a hidden intermediate mass black hole in the system, its gravity subtly bending the signal like a cosmic funhouse mirror. The implications were staggering. If true, it would mean the signal wasn't just artificial, it might have been filtered through one of the universe's most destructive phenomena. Yet as quickly as the hype built, it crumbled under scrutiny. Further analysis revealed the signal's drift matched radio interference from human technology, likely a passing satellite or ground-based device. By 2021, BLC-1 was officially dismissed as terrestrial noise. But here's why this false alarm still matters. The episode exposed how black holes could theoretically distort artificial signals in ways we're only beginning to understand. Imagine an advanced civilization broadcasting near a black hole. Its gravity might stretch or compress their transmissions, creating eerie frequency shifts that mimic natural phenomena. The BLC-1 saga leaves us with a haunting question. How many genuine signals have we already overlooked because they were twisted beyond recognition by unseen black holes? As we keep listening to the stars, we're not just hunting for alien greetings, we're learning to decode the universe's most enigmatic eavesdroppers, one gravitational whisper at a time. Deep in the heart of our Milky Way, where stars crowd together like fireflies in a jar, something is broadcasting a signal that shouldn't exist. For decades, astronomers have detected bizarre, looping radio waves swirling out from the Galactic Center, right where Sagittarius A, our galaxy's supermassive black hole, holds court. These aren't the steady hum of ordinary cosmic noise. They're twisted, filament-like structures stretching dozens of light years, pulsing with energy that defies every textbook model of black hole behavior. What makes these filaments so perplexing? First, their shape. Unlike the chaotic jets blasting from other black holes, these formations are eerily organized, like cosmic harp strings vibrating with some unseen force. Second, their longevity. While most energetic phenomena in space flare and fade quickly, these filaments have persisted for thousands of years, threading through the galactic core like ghostly scars. The leading theory suggests they're caused by interactions between Sagittarius A's magnetic fields and the torrent of high-energy particles trapped in its orbit. Picture the black hole as a colossal dynamo, spinning so fast it twists space-time itself. generating magnetic tornadoes that whip surrounding plasma into these bizarre glowing tendrils. But the anomalies run deeper. In 2019, astronomers discovered something even stranger: flickering hotspots along the filaments, pulsing with a rhythm that matches nothing in known physics. Some pulses last minutes, others vanish in seconds. One particularly haunting clue: the hotspots appear to move not at the leisurely pace of orbiting matter, but at speeds approaching light itself. This has sparked wild new theories like cosmic strings vibrating near the black hole's event horizon, or even echoes of primordial wormholes left over from the Big Bang. Yet the greatest mystery might be what we aren't seeing. Despite Sagittarius A's colossal size, 4 million times heavier than our Sun, it's oddly quiet compared to other supermassive black holes. These filaments could be the key to why. Some researchers suggest they're siphoning energy away from the black hole, acting like cosmic lightning rods to stabilize its outbursts. Others propose they're evidence of past eruptions, relics of a time when our galaxy's heart roared with unfathomable violence. Either way, one thing's certain: Sagittarius isn't sleeping. It's whispering, and the signals it leaves behind are rewriting the story of how black holes shape the galaxies they call home. Some black holes don't just whisper, they beat. 500 million light-years from Earth, in the constellation Aquila, astronomers have detected something spine-tingling: a black hole with a pulse. Designated JARES 19151105, this voracious cosmic predator is locked in a deadly dance with a companion star, siphoning off its gas in a swirling accretion disk. But what makes it extraordinary isn't just its appetite. It's the rhythmic X-ray flashes erupting from its core like clockwork, every 67 seconds for decades. Scientists call it the black hole heartbeat, and it's the most stable high-energy rhythm ever observed in the cosmos. At first glance, the heartbeat seems like a simple cosmic metronome, matter heating to millions of degrees as it spirals inward, emitting X-rays with each rotation. But here's the problem: black holes aren't supposed to have structure. Their event horizons are, by definition, the ultimate smooth criminals. No bumps, no ridges, nothing to stick to and create regular pulsations. Yet this one's heartbeat persists unwavering for years at a time, then vanishes for months before returning just as strong. It defies every model of how black hole accretion should work. The leading theory involves a ghostly fingerprint of the black hole's spin. Some researchers suggest the heartbeat is caused by relativistic effects near the event horizon, where space itself is dragged around the black hole like syrup stirred by a spoon. In this scenario, clumps of gas in the inner disk could be whipped into periodic flares by the black hole's rotation, like a lighthouse beam slicing through fog. Others propose even weirder physics: vibrating magnetic field lines snapping and reconnecting like cosmic rubber bands, or shockwaves bouncing between the disk and the black hole's corona like echoes in a cavern. But the real mystery lies in the heartbeat stability. Most black hole fluctuations are chaotic, changing on timescales of milliseconds. This 67-second rhythm, though, it's precise enough to set your watch by. Even more bizarre when the signal disappears, as it did mysteriously between 1996 and 2000. It returns later with the exact same period, as if some unseen cosmic conductor kept counting the beats in silence. That kind of persistence suggests something far stranger than random turbulence: a hidden structure, perhaps, or a resonance between the black hole's spin and the dying star feeding it. Could this be evidence of a Planck star, a theoretical remnant of a black hole's birth hiding just beneath the event horizon? Or is it proof that black holes can sustain oscillations like a drumhead ringing across the universe? Each pulse is a siren song from the edge of the unknowable, daring us to decode its rhythm. And as long as it keeps beating, we'll keep listening, because every tick might be a clue to what really happens when space and time collapse into infinity. Gamma rays are the universe's deadliest fireworks, blinding bursts of energy that can outshine entire galaxies in a heartbeat. But hidden among these cosmic detonations are flashes that shouldn't exist. Gamma ray signals with no visible source, erupting from patches of empty space like phantom explosions. These aren't your ordinary gamma ray bursts from colliding neutron stars or supernova. These are ghosts in the machine, events so powerful they can be detected across billions of light years, yet leave no trace of their origin. And some of them point squarely at black holes. Take JABI 070610, a gamma-ray flare detected in 2007 that defies all logic. Lasting a staggering 102 seconds, an eternity for such events, it blasted from a region of space with no known galaxies, no star clusters, nothing to explain its apocalyptic energy output. Here's the twist. Years later, astronomers found an invisible gravitational anomaly right where the burst originated. Not a star, not a nebula, but something massive enough to bend light around it. The best guess, a rogue black hole drifting through intergalactic space like a cosmic highwayman, shredding some unseen victim and lighting up the void with gamma-ray screams. The energy levels involved are beyond comprehension. These unidentified flashes often pack more punch in seconds than our sun will emit in its entire 10 billion-year lifetime. Yet they vanish without leaving the usual debris, no afterglow in X-rays or visible light, no expanding shockwave. It's as if the universe flicked a switch, unleashed hell, then erased all evidence. The leading theory involves orphaned gamma-ray bursts, events where the jet of energy is aimed directly at Earth, hiding the source like a flashlight beam shining in your eyes. But even that doesn't fully explain why so many align with regions where gravitational lensing suggests hidden black holes lurk. Detection is its own nightmare. Gamma rays don't play nice with telescopes. They pass right through most materials, requiring orbiting detectors like NASA, a Fermi gamma-ray space telescope, to catch them. And the timing couldn't be more cruel. These flashes often last mere milliseconds, leaving scientists scrambling to trace their origin before they disappear forever. Some seem to repeat from the same patch of sky months or years apart, hinting at cyclical black hole activity. Others are one-time enigmas, cosmic gunshots with no smoking gun. What could possibly generate such violent yet invisible eruptions? One provocative idea involves dark matter annihilation, theoretical particles colliding and obliterating each other near a black hole's event horizon. Another suggests black holes spinning so fast they become cosmic particle accelerators, flinging matter outward at near light speed until it smashes into itself, detonating in gamma-ray fireballs. Then there's the most unsettling possibility of all, intermediate mass black holes, the elusive, missing link between stellar and supermassive varieties, may be triggering these bursts as they feast on dense molecular clouds we can't yet observe. Every unexplained gamma-ray flash is a cosmic crime seen with no body, no weapon, and no witness, just the echo of something monstrous happening in the dark. And as our detectors grow more sensitive, the mystery only deepens. For every burst we trace to a colliding star or dying galaxy, another dozen remain stubbornly anonymous, whispering the same terrifying question: what else is out there, hiding in plain sight, capable of bending the very fabric of reality to its will? Picture the universe stretching endlessly in all directions, galaxies scattered like dust, drifting on the currents of cosmic expansion. But what if this grand cosmic dance isn't as random as it seems? In 2008, astronomers studying the microwave glow of the Big Bang stumbled onto something that sent chills through the scientific community. A mysterious, uniform tug dragging entire galaxy clusters toward the constellation Centaurus at nearly 2 million miles per hour. They called it the dark flow, and if real, it suggests something inconceivable: black holes so vast, so powerful, they're bending the fabric of the cosmos itself. The evidence comes from subtle distortions in the cosmic microwave background, the afterglow of the Big Bang. Normally, this radiation is nearly uniform, a relic of the universe's infancy. But when researchers mapped the motion of over 700 galaxy clusters, they found a startling pattern. Clusters moving together, all pulled in the same direction, as if some unseen hand were herding them. The kicker: these clusters span billions of light years, far too distant for any known force in our observable universe to influence them. The leading culprit: supermassive black holes beyond our cosmic horizon, so enormous their collective gravity warps spacetime on a scale we can barely fathom. Critics have pushed back hard. Some argue the dark flow could be a statistical fluke, a ripple in the data mistaken for motion. Others propose less exotic explanations, like uneven expansion from the Big Bang's aftermath. But here's what keeps theorists awake at night. If the dark flow is real, it implies the existence of structures so colossal they redefine our understanding of reality. We're talking about black holes or something even stranger existing outside the observable universe, their gravitational reach stretching across unfathomable distances to yank galaxies like puppets on strings. The implications are staggering. Could our universe be just one bubble in an infinite multiverse, with these phantom black holes lurking in neighboring cosmic realms? Or is there a previously unknown layer to gravity itself, a hidden force that links the cosmos in ways Einstein never predicted? The dark flow remains one of astronomy's most divisive mysteries, a signal without a source, a question without an answer. And until we peer deeper into the void, it stands as a haunting reminder: the universe may be playing by rules we haven't even discovered yet. There's a black hole in the Perseus galaxy cluster that doesn't just swallow stars, it sings. 250 million light-years away, NASA Chandra X-ray Observatory picked up something extraordinary: pressure waves rippling through the superheated gas around the galaxy's central black hole, creating a note so deep it's 57 octaves below middle C. That's a frequency 1,000,000 billion times lower than anything the human ear could detect, until scientists scaled it up, revealing a haunting interstellar hum. This isn't just cosmic noise. These sound waves are the aftermath of a feeding frenzy, the black hole's gravity sloshing surrounding gas like water in a bowl, creating rhythmic pulses that travel hundreds of thousands of light years. The pitch is unnervingly stable, a B-flat sustained for over 2 billion years. To put that in perspective, if a piano key could play for that long, it would still be echoing when Earth's continents were nothing but molten rock. But here's where it gets stranger. These waves aren't just eerie background music, they're heating the galaxy cluster. Normally, gas this dense should cool and collapse into new stars, but the black hole's melody keeps it simmering like a pot on low boil. Astronomers call it feedback, a self-regulating system where the black hole's growl prevents its own feast from growing too cold. It's a cosmic balancing act, one that might explain why some galaxies stop forming stars long before they run out of fuel. Yet mysteries linger. Why this particular note? Why doesn't the sound dissipate over such vast distances? Some theorists suspect the black hole's spin acts like a phonograph needle, etching vibrations into spacetime itself. Others propose the waves are amplified by dark matter, an invisible conductor orchestrating the chaos. One thing's certain: this isn't just a black hole's idle noise. It's a lullaby for an entire galaxy, a force shaping the cosmos one deep, unending note at a time. And somewhere in that hum, there might be clues to how the universe tunes its grandest symphonies. Rising like colossal, ghostly hourglasses from the Milky Way's core, the Fermi bubbles are one of the most jaw-dropping structures ever discovered in our galaxy, and no one saw them coming. Stretching 25,000 light-years above and below the galactic plane, these twin lobes of scorching hot gas and gamma radiation were invisible until 2010, when NASA's Fermi Gamma Ray Space Telescope peeled back the curtain on their existence. What astronomers found defied imagination. Two vast, symmetrical bubbles of energy, their edges razor-sharp, as if someone had used cosmic scissors to carve perfect shapes into the fabric of space. And at their base, none other than Sagittarius A, the supermassive black hole squatting at the heart of our galaxy. The sheer scale of these structures is breathtaking. If you could see them with the naked eye, they'd span half the night sky, each bubble large enough to swallow 1,000 solar systems whole. Their energy output is equally staggering, glowing with gamma rays millions of times more energetic than visible light. But the real mystery lies in their origin. How could a black hole, even one as massive as Sagittarius A, create something so enormous, so perfectly balanced without tearing the galaxy apart? The leading theory is a cataclysmic feeding frenzy. About 3.5 million years ago, Sagittarius A may have gorged on an immense cloud of gas or a wayward star cluster, triggering a violent outburst. As matter spiraled into the black hole's maw, twin jets of superheated plasma could have shot outward at near light speed, punching through the galactic disk and inflating these gargantuan bubbles like cosmic balloons. Supporting this idea are strange, glowing filaments found along the bubble's edges, magnetic stitch marks that might trace the paths of ancient shockwaves. Yet not everyone's convinced. Some researchers argue the bubbles are too symmetrical, too clean, to result from a chaotic black hole eruption. Alternative explanations range from the aftermath of a burst of star formation near the Galactic Center to the annihilation of invisible dark matter particles. There's even a fringe hypothesis that they're scars from a long-ago collision with a dwarf galaxy, its remnants stirred into a glowing frenzy by Sagittarius A's gravity. The most tantalizing clue comes from the bubble's chemistry. Spectroscopic studies reveal they're laced with heavy elements like iron and silicon, the cosmic ashes of exploded stars. This suggests a direct link to the black hole's activity, as it could have hurled stellar debris outward in a titanic belch of energy. But here's the twist: the bubbles aren't just relics. They're still crackling with activity, their gamma-ray emissions flickering in ways no model fully explains. Could we be witnessing the aftermath of a black hole's meal, or the prelude to its next one? The Fermi bubbles stand as silent sentinels, guarding secrets about our galaxy's violent past and its uncertain future. And as telescopes grow more powerful, these ghostly giants may finally reveal just how much power a sleeping supermassive black hole can really wield. Our universe has a case of missing matter, baryonic matter, to be precise, the ordinary stuff that makes up stars, planets, and even us. According to all our calculations, about a third of it has simply vanished. This is the missing baryon problem, a cosmic detective story that gets even stranger when we look at black holes. These gravitational monsters seem to be hiding more than just light. They might be swallowing the very fabric of reality itself. Take the Milky Way. When astronomers tally up all the visible stars, gas, and dust, they come up short by about half. The missing matter isn't dark matter or some exotic particle. It's protons, neutrons, electrons, the same stuff we're made of. So where did it go? One leading suspect: supermassive black holes. Not because they're hoarding it, but because they're warping it into forms we can't detect. When matter spirals into a black hole's accretion disk, it doesn't just vanish. It's heated to millions of degrees, shredded into plasma, and accelerated to near light speed. Under these conditions, ordinary matter might transform into faint, diffuse clouds of ultra-hot gas, invisible to most telescopes, but the plot thickens. Some of this missing matter could be hiding in plain sight, stretched into cosmic filaments, vast, thread-like structures of gas connecting galaxies. Black holes might be the engines behind these invisible highways, spewing out matter in colossal winds or jets that weave through intergalactic space. Simulations show that black hole feedback, the energy they unleash while feeding, can push baryons far beyond their host galaxies, scattering them so thinly they're nearly impossible to spot. Here's where physics gets shaky. The laws governing how matter behaves under extreme gravity, especially near black holes, are still full of gaps. Quantum mechanics and general relativity clash at the event horizon, meaning we might be missing a fundamental piece of the puzzle. Could some baryons be crushed into unknown states or trapped in a quantum fog at the edge of oblivion? The answer might rewrite our understanding of both black holes and the universe's missing inventory. The hunt for these lost baryons is forcing us to rethink everything. New telescopes like the X-RISM satellite are scanning the skies for faint X-ray whispers from hidden gas clouds. Others are searching for distortions in the cosmic microwave background, tiny imprints left by wandering matter. Each clue brings us closer to solving the mystery, but one thing's certain: black holes aren't just destroyers. They're cosmic alchemists transforming the familiar into something utterly unrecognizable. And in their shadow, the universe keeps its most stubborn secrets. Stephen Hawking's greatest theoretical breakthrough might also be his most frustrating, because it's the one cosmic prediction we still can't prove. Back in 1974, the legendary physicist dropped a bombshell: black holes shouldn't be completely black. Instead, they should slowly leak energy, emitting what's now called Hawking radiation. This faint glow, he argued, would eventually cause black holes to evaporate entirely, vanishing in a final puff of quantum fireworks. It was a stunning idea, one that bridged Einstein's gravity with quantum mechanics for the first time. But nearly 50 years later, we've never detected a single photon of this radiation. So where is it? The math behind Hawking radiation is devilishly elegant. According to quantum theory, empty space isn't really empty. It's a seething foam of virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other instantly. But near a black hole's event horizon, Hawking realized gravity could wrench them apart, with one particle falling in while the other escapes. The escaping particles would carry away energy, making the black hole lose mass over time. For stellar mass black holes, the effect is absurdly weak, a trickle of photons so faint they'd be drowned out by the cosmic microwave background. But for tiny, primordial black holes forged in the Big Bang's chaos, Hawking radiation should be explosive, even visible. The catch: we've found zero evidence these miniature black holes exist. Some physicists argue we're simply not looking in the right way. Hawking radiation's wavelength is inversely proportional to the black hole's size, meaning most emissions would be in uselessly long radio waves or undetectably high-energy gamma rays. Others propose that intervening dust or magnetic fields might scatter the signal beyond recognition. Then there's the time problem. A solar mass black hole would take 10 to the power of 67 years to evaporate. On human timescales, its radiation would be quieter than a whisper in a hurricane. But what if the paradox runs deeper? Recent work in string theory and loop quantum gravity suggests Hawking's original calculation might be incomplete. Some models predict that radiation stops carrying information once the black hole shrinks beyond a certain point, violating quantum mechanics' sacred rule that information can't be destroyed. Others argue that event horizons might not function as Hawking imagined. Perhaps quantum effects create a firewall that burns up incoming particles, altering the radiation spectrum entirely. The most radical idea, that Hawking radiation doesn't exist at all, and black holes truly are eternal. The stakes couldn't be higher. If Hawking radiation is real but invisible, it implies our detectors just aren't sensitive enough yet. But if it's fundamentally undetectable, we might need to rewrite quantum theory itself. Either way, this elusive signal remains one of cosmology's greatest unsolved puzzles, a ghostly whisper from the edge of physics, taunting us to listen harder. When two black holes collide, the universe doesn't just shudder, it sings. The gravitational waves from these cataclysmic mergers ripple through space-time like a stone dropped in a pond, ringing out with frequencies we can now detect. But sometimes there's an encore, an eerie, delayed echo that shouldn't exist. These aren't just cosmic reverberations, they're glitches in the fabric of reality, challenging everything we thought we knew about how black holes behave in their final, violent moments. Take GW150914, the gravitational wave signal detected by LIGO in 2015. At first glance, it fit the textbook model, two black holes spiraling inward, merging in a split-second burst of energy. But then, buried in the data, scientists found something bizarre: tiny, faint pulses arriving after the main event, like footsteps echoing in an empty hallway long after the door has slammed shut. These weren't random noise, they were precise, repeating distortions, as if space-time itself had developed a memory of the collision, the leading explanation. A phenomenon called gravitational wave echoes, where some of the energy from the merger bounces off an unseen boundary near the black hole's event horizons. Think of it like shouting into a canyon and hearing your voice return, except this canyon is a warped pocket of reality where gravity twists space into knots. The echoes suggest something revolutionary, that black holes might not have smooth, featureless event horizons as Einstein predicted, but instead are surrounded by quantum fuzz, a turbulent zone where spacetime behaves more like a choppy ocean than a still pond. But here's where the mystery deepens. These echoes don't align with standard black hole models. Their timing and intensity imply structures outside the event horizon, exotic objects like wormholes, gravastars, or even remnants of collapsed higher dimensional space. Some theorists propose these echoes could be evidence of a firewall, a hypothetical ring of searing energy just beyond the event horizon that scrambles incoming matter into pure radiation. Others wonder if we're seeing the first hints of a theory of quantum gravity, where spacetime itself is pixelated and black holes leave behind faint, looping imprints of their violent birth. The implications are staggering. If these echoes are real, they could rewrite our understanding of black holes as cosmic vacuum cleaners, revealing them instead as complex, layered objects with hidden structures. Every delayed pulse is a clue, a breadcrumb leading us closer to answering one of physics' biggest questions. What really happens to matter and energy when they cross the point of no return? Until we unravel these echoes, one thing's certain: black holes aren't just silent killers. They're storytellers, whispering secrets in a language of warped spacetime we're only just beginning to decode. Quasars are supposed to be the universe's lighthouses, steady beacons blazing from the centers of distant galaxies, powered by supermassive black holes feeding on endless streams of gas. But something's wrong with some of them. Astronomers have spotted quasars flickering like candle flames in the wind, their brightness surging and plunging with no rhyme or reason. This isn't the gentle pulsing of matter spiraling into a black hole's maw. This is chaos. Take quasar J0435 plus 6126, a cosmic enigma 3 billion light-years away. In just 2011, its brightness shot up by 60% in less than 48 hours, a change that, by conventional physics, should take centuries to unfold. Theories crumble under behavior this extreme. Normally, a quasar's accretion disk, the swirling ring of superheated gas around its central black hole, operates like a well-oiled machine. Variations happen gradually as changes in the disk's density or magnetic fields ripple outward at speeds limited by physics. But what could make an entire quasar dim or brighten almost overnight? One possibility: hidden black holes stirring the pot. Some models suggest these erratic quasars might harbor two supermassive black holes locked in a gravitational tango, their orbits yanking the accretion disk like a cosmic yo-yo. Every close pass could trigger violent outbursts, flinging matter into the primary black hole in sudden, unpredictable gulps. Then there's the case of Quasar Assassin 14 Li, which didn't just fluctuate, it erupted. In 2014, astronomers watched as it brightened by a factor of 50 over 9 months, then faded just as mysteriously. The smoking gun, a rogue star strayed too close to the black hole and was torn apart, a tidal disruption event that flooded the accretion disk with fresh fuel. But here's the twist. Assassin 14 Lies flares came in repeating bursts like clockwork every 270 days. That kind of precision suggests an invisible puppeteer, perhaps a second black hole, its gravity stirring the debris into regular, explosive crescendos. The real head-scratcher is how these signals reach us at all. Light from the inner edge of a quasar's accretion disk has to travel through the rest of the disk, then through interstellar gas and dust before finally streaming across the universe to our telescopes. Any flickers should be smeared out by the journey, like a light bulb's glow dimmed by fog. Yet these quasars pulse sharply, as if their light is slipping through some cosmic backdoor. Some theorists speculate the answer lies in Doppler beaming, where jets of matter blasted outward at near light speed act like celestial strobe lights. As the jets twist and turn, their emissions can appear to flash in our direction, amplifying the quasar's glow in erratic bursts. But perhaps the most unsettling implication is what these signals say about black holes themselves. If quasars can flicker like faulty street lamps, then our understanding of their engines, black holes operating at the so-called Eddington limit, the maximum stable feeding rate, might be fundamentally flawed. Could black holes binge and starve in cycles we've never witnessed? Or are we seeing the fingerprints of new physics where spacetime itself becomes unstable near the event horizon? Every erratic quasar is a cosmic wild card, reminding us that even the brightest monsters in the universe still have secrets to spill. And as our telescopes grow sharper, these flickering enigmas might just rewrite the rules of the cosmos. Among the countless particles streaming through the universe, neutrinos are the ultimate ghosts. Billions pass through your body every second without a trace. These nearly massless particles barely interact with matter, making them astronomically difficult to detect. Yet in recent years, scientists have managed to catch extremely high-energy neutrinos and, against all odds, trace some back to cosmic monsters, black holes. This achievement isn't just a technical marvel, it's rewriting the playbook on how we study the universe's most violent phenomena. The breakthrough happened deep under the Antarctic ice, where the Ice Cube Neutrino Observatory lies buried like a cosmic listening post. When a high-energy neutrino rarely collides with an atom in the ice, it creates a faint blue flash called Cherenkov radiation. On September 22, 2017, IceCube detected a neutrino with energy so staggering it could have powered a small city. Named IceCube 170922A, this single particle set off a global hunt to pinpoint its origin. Telescopes swiveled toward the coordinates, and there, in the constellation Orion, they found something extraordinary. A blazing active galaxy called TXS 0506+056, its core a supermassive black hole spewing jets of plasma at near light speed. Here's why this matters. Neutrinos, unlike light or radio waves, travel in straight lines across the universe, unaffected by magnetic fields or interstellar dust. That makes them perfect cosmic messengers if we can catch them. Tracing one back to a black hole is like finding a single fingerprint at a crime scene that leads you straight to the culprit. In this case, the culprit was a blazar, a galaxy whose black hole's jet happens to be aimed directly at Earth. Scientists suspect the neutrino was forged in the jet's hellish environment, where protons accelerated to unimaginable energies collide and shatter into subatomic shrapnel, including neutrinos. But the plot thickens. Not all high-energy neutrinos come from such obvious sources. Some arrive in clusters like cosmic breadcrumbs leading to regions where black holes lurk unseen. In 2022, IceCube detected a flurry of neutrinos from the direction of NGC 1068, a galaxy with a quiet supermassive black hole, one not actively feeding or emitting jets. This raises a tantalizing possibility. Even sleeping black holes might generate neutrinos through hidden processes, perhaps via stealthy interactions with dark matter or quantum fluctuations near their event horizons. The implications ripple far beyond astrophysics. neutrinos could be the key to solving one of cosmology's biggest puzzles: the origin of ultra-high-energy cosmic rays, particles that hit Earth with energies 1,000,000 times greater than anything our most powerful colliders can produce. Black holes have long been suspects, but cosmic rays, being charged particles, zigzag through magnetic fields obscuring their origins. Neutrinos, being neutral, don't have this problem. Every high-energy neutrino we trace back to a black hole isn't just a scientific triumph, it's a roadmap to the universe's most extreme particle accelerators. Yet for every answer, new questions emerge. Why do some black holes produce neutrino floods while others, seemingly identical, remain silent? Could neutrinos reveal previously unknown black hole behaviors, like microscopic quantum fireworks at the event horizon? And most hauntingly, what else might these ghostly particles tell us as our detectors grow more sensitive? One thing's certain: in the silent streams of neutrinos piercing the cosmos, black holes are leaving fingerprints we're only just beginning to read. Dark matter is the universe's greatest vanishing act, an invisible substance that outnumbers ordinary matter 5 to 1, its presence betrayed only by the way it tugs on galaxies with unseen fingers. For decades, scientists have hunted for its true nature, from ghostly particles to hidden dimensions. But what if the answer has been lurking in plain sight, hidden in the darkest corners of the cosmos? Enter one of the most provocative theories in modern astrophysics: the idea that black holes and dark matter might be two sides of the same cosmic coin. The clues start with gravity. Galaxies spin so fast they should fling stars into the void, yet something holds them together. That something is dark matter's gravitational glue. But here's the puzzle: when astronomers map where this invisible mass clusters, they often find it suspiciously aligned with black holes. Take the Milky Way's center. The supermassive black hole Sagittarius sits in a gravitational well far deeper than its visible mass can explain, as if something massive but unseen is anchored to it. Similar anomalies appear in dwarf galaxies, where black holes seem unnaturally heavy for their tiny stellar neighborhoods. The math is clear: something's missing. One radical solution: primordial black holes, hypothetical relics from the Big Bang's first chaotic seconds. Unlike black holes born from dying stars, these would range from asteroid size to planet mass, peppering the cosmos like invisible buckshot. If they exist in vast numbers, they could account for dark matter's gravitational fingerprints without needing exotic particles. Recent studies of gravitational lensing, where distant light bends around unseen mass, hint at this possibility. In 2018, the Subaru telescope spotted brief, star-like twinkles in ancient galaxy clusters, possibly caused by primordial black holes drifting in front of background stars. The timing matches predictions for a hidden population of these objects, but the plot twists further. Some theorists suggest dark matter isn't just near black holes, it's feeding them. Certain models propose that dark matter particles, if they exist, could collect in dense halos around black holes, occasionally colliding and annihilating into gamma rays. This might explain mysterious energy flares from quiet black holes, like those seen in the Fermi Gamma Ray Space Telescope's data. Even stranger, if dark matter interacts weakly with itself, it could form dark disks around black holes, warping their accretion disks in ways that defy standard physics. Skeptics aren't convinced. The primordial black hole theory has glaring holes, literally. If they were abundant enough to explain dark matter, we'd see more gravitational lensing events than observed. Others argue that black holes and dark matter simply share the same cosmic neighborhoods because both favor dense regions, like streetlights clustering in cities. The debate rages, but one thing's certain: every unexplained wobble in a star's orbit, every anomalous lensing signal, and every too heavy black hole is a breadcrumb, one that might lead us to the darkest secret the universe has been keeping. Black hole jets are supposed to follow the rules, blasting outward along the spin axis of their accretion disks like cosmic fire hoses locked in place. But out in the distant universe, some jets are breaking rank, pointing in directions that make astrophysicists question everything they thought they knew about how black holes feed. Take the bizarre case of Galaxy NGC 1277, home to a supermassive black hole with an appetite for chaos. Instead of firing twin jets perpendicular to its disk, this monster sends them shooting off at a skewed angle, as if the entire system were tipped on its side. Even stranger, the jets process, wobbling like a slowing top over tens of millions of years' behavior that defies all standard models of black hole mechanics. What could possibly wrench these jets out of alignment? One leading theory points to hidden black holes stirring the pot. Simulations show that if a second supermassive black hole orbits the primary one, their gravitational tug of war could torque the accretion disk, tilting it like a vinyl record warped in the sun. The jets, anchored to the disk's orientation, would then skew wildly off-axis. Supporting this idea are eerie gaps spotted in some accretion disks, clean, dust-free lanes that suggest something massive is clearing a path, perhaps a companion black hole carving its way through the chaos. But there's a catch. For the jets to stay misaligned, the disk itself would need to resist the natural pull of the black hole's gravity, which should, over time, force everything back into orderly planes. This has led to even wilder proposals, like magnetic fields so powerful they lock the disk in place like a fly in amber. In 2022, the Event Horizon Telescope caught hints of this in Galaxy M87, where the base of its famous jet appears kinked, as if something invisible, perhaps a cage of magnetic force, is bending it against the will of gravity. The real shocker came with the discovery of counter-rotating disks, where the inner and outer regions spin in opposite directions like gears grinding against each other. In these systems, jets can spiral outward in corkscrews, their paths tangled by the disk's internal war. How these disks form remains a mystery, though some speculate they're the aftermath of galactic mergers, where two black holes' accretion disks collide and merge at odd angles, leaving behind a system that spins in fragments. Every misaligned jet is a cosmic rebellion, a middle finger to the neat diagrams in astrophysics textbooks. They force us to confront how little we truly understand about the chaos swirling just beyond a black hole's event horizon. And as telescopes peer deeper, one thing becomes clear when it comes to these gravitational monsters. The universe has a flair for the unpredictable. Some black holes defy the cosmic diet plan. They binge on matter at rates so extreme they shouldn't physically exist. Take the behemoth at the heart of Quasar Ton 618, a supermassive black hole clocking in at 66 billion times the mass of our Sun. According to standard models, black holes this size should take billions of years to form, slowly nibbling on gas and stars. But Ton 618 exists in a universe only 1 billion years old, meaning it grew to galactic heavyweight status 10 times faster than physics should allow. Astronomers call these cosmic anomalies overfed black holes, and their existence is tearing up the rulebook on how gravitational monsters grow. The mystery deepens when you look at their feeding habits. Black holes are messy eaters as matter falls toward them. It heats up and radiates energy, creating pressure that should blow away potential food before too much can be consumed. This natural braking system, called the Eddington limit, keeps black holes from growing too quickly. But overfed black holes like the one powering quasar SDSS J0100 plus 2802 laugh in the face of this limit. In 2015, observations revealed it was swallowing matter at 500 times the Eddington rate, packing on mass equivalent to a sun every day. How do they cheat the system? One radical theory suggests these black holes might have started life as seeds far larger than we thought. Primordial monsters forged in the Big Bang's aftermath, already weighing thousands of solar masses when the universe was in its infancy. Another idea involves cosmic conveyor belts, dense, fast-moving streams of gas that plunge directly into the black hole's maw before radiation pressure can push them away. Recent simulations show that in the early universe's chaotic environment, these rivers of cold gas could have flowed unabated into waiting gravitational pits, fueling freakish growth spurts. But the real curveball comes from black holes like Euler's J134+005, which not only grew too fast, but did so without the luminous fireworks we'd expect. Normally, a black hole eating this much would shine brighter than an entire galaxy, yet some overfed giants remain oddly dim. This silent feasting hints at an entirely new consumption mode, perhaps matter falling in nearly radially, minimizing friction and light production. Or worse, our models of accretion physics might be missing fundamental pieces of how space-time behaves under such extreme conditions. What's clear is this: overfed black holes aren't just cosmic oddities. They're smoking guns pointing to gaps in our understanding of gravity's most extreme regime. Every time we find one of these rule breakers, it forces us to reconsider what's possible in the dark heart of a galaxy. And as telescopes peer deeper into the early universe, we're left with a haunting question: just how many more of these gravitational gluttons are lurking in the shadows, rewriting the laws of physics with every meal? Some black holes prefer to lurk in the shadows, quiet, unassuming, almost invisible. But every so often, without warning, they erupt in violent tantrums of light and energy. These aren't the steady glows of feeding supermassive black holes or the predictable pulses of merging binaries. These are sudden, savage flares, bursts of X-rays and gamma rays so intense they can outshine an entire galaxy for a few terrifying minutes. And the most baffling part, they come from black holes that, by all accounts, should be dormant. Take Swift J1644+575. In 2011, this sleeping giant, a black hole roughly 20 times the mass of our Sun, awoke with a vengeance. Over just 48 hours, its X-ray emissions spiked by a factor of 10,000, bathing nearby space in a lethal glow before fading back into obscurity. Similar flares have been spotted in galaxies like NGC 4939, where a supermassive black hole suddenly roared to life after decades of silence. Its outburst so powerful it briefly dwarfed the collective light of billions of stars. So what triggers these cosmic temper tantrums? The prime suspect: tidal disruption events, where a star strays too close and gets shredded into a glowing stream of plasma. As the black hole feasts on this stellar spaghetti, the infalling matter heats up, creating a short-lived but brilliant flare. Evidence comes from flares like Assassin 15LH, where astronomers caught the telltale fingerprints of hydrogen and helium in the light spectrum, debris from a star ripped apart mid-plunge. But not all flares fit this neat narrative. Some, like those from the black hole V404 Cygni, flicker wildly, pulsing every few minutes, far too fast for a star's leisurely destruction. Others emit oddly collimated beams of energy, as if channeled by some unseen cosmic nozzle. This has led to an alternative culprit: magnetic reconnection. Near a black hole's event horizon, magnetic fields can twist into knots so tight they snap, releasing pent-up energy in explosive bursts like a rubber band stretched until it fires off a pulse of raw power. The debate gets murkier with flares from supermassive black holes like Sagittarius A. In 2019, it flared inexplicably bright for a few hours, yet no star was seen falling in. Instead, its light curve matched simulations of magnetic reconnection in the turbulent plasma near the event horizon. Then again, in 2022, another flare from the same black hole showed chemical signatures more consistent with a shredded gas cloud. Could both mechanisms be at play? Some theorists suggest black holes might switch between feeding modes, sometimes gorging on stars, other times snacking on magnetic energy. There's even a wild-card possibility: quantum effects near the event horizon creating particle-antiparticle bursts that ignite these flares. Until we catch one in the act with next-generation telescopes, these eruptions remain cosmic whodunits, each violent outburst a clue to the chaotic physics unfolding where gravity rules supreme. At the outermost edges of theoretical physics lies a concept so strange it sounds like science fiction, the idea that space-time itself might not be smooth, but pixelated, like a cosmic photograph blown up until you see the grain. This is the holographic principle, a radical notion suggesting that all the information in our three-dimensional universe could be encoded on a two-dimensional surface like a hologram. And if this theory holds, black holes might be broadcasting the evidence in a faint, chaotic hum scientists call holographic noise. The theory stems from a startling paradox about black holes. When matter falls into one, it seemingly vanishes, taking all its information with it. A direct violation of quantum mechanics' ironclad rule that information can never be destroyed. To resolve this, some physicists propose that the event horizon isn't just a boundary. It's a frenetic, vibrating membrane where quantum bits of information jostle like static on an old TV. These vibrations, if real, would create a subtle crackle in space-time, a noise that carries the fingerprints of the universe's underlying pixelation. Hunting this noise isn't for the faint of heart. In 2015, a team at the Fermilab Holometer aimed to catch it by splitting laser beams and measuring whether space-time's supposed pixels caused infinitesimal jitters in the light's path. The results were inconclusive, but the effort opened a door. Newer experiments, like the proposed Quest facility in Germany, plan to use ultra-precise atomic interferometers, devices so sensitive they can detect ripples in space-time 1,000 times smaller than an atomic nucleus. What makes this search so electrifying is the stakes. If holographic noise exists, it would mean reality as we know it is fundamentally grainy, with a resolution limit set by the Planck length, the smallest possible unit in the universe. Black holes, as cosmic information processors, would be the ultimate test beds, their event horizons the most likely places for this quantum static to leave traces. Skeptics argue the noise could just be instrumental artifacts or quantum fluctuations unrelated to spacetime's structure. But believers counter that the noise's specific frequency spectrum, predicted to follow a distinct mathematical pattern called 1/f noise, could be the smoking gun. Future detectors tuned to this signature might finally hear the universe's hidden code, crackling through the void like a radio tuned between stations. Whether holographic noise is real or not, the quest to find it forces us to confront the deepest question of all. Is the cosmos continuous, or is it, at some unfathomably tiny scale, a mosaic of discrete pieces? And if so, could black holes be the universe's way of whispering to us in pixels, not waves? If black holes are cosmic vacuum cleaners, relentlessly devouring everything in their path, then white holes are their hypothetical opposites, cosmic fire hydrants spewing out matter and energy with unstoppable force. The idea sounds like pure science fiction, but it emerges straight from the math of general relativity. Just as black holes have event horizons where nothing can escape, white holes would have boundaries where nothing can enter. And some theorists suggest these bizarre objects might be behind a handful of the universe's most puzzling signals. Take gamma-ray burst GRB 060614, a fleeting explosion of energy that appeared in 2006. Unlike most gamma-ray bursts which fade predictably, this one flared with a strange, symmetrical light curve, almost as if something had ejected a perfectly timed burst of energy and then slammed shut. Intriguingly, the signal's spectrum didn't match the messy aftermath of a collapsing star or colliding neutron stars. Instead, it bore eerie similarities to simulations of white holes burping out trapped matter in one violent ejection. The controversy lies in the details. For white holes to exist, they'd need some mechanism to form in the first place. One possibility is that they're the other end of black holes, connected by wormholes in a hypothetical process called quantum bouncing. Under this model, matter falling into a black hole could emerge from a white hole in another part of the universe, or even another time. But here's the catch. White holes violate the second law of thermodynamics, which dictates that entropy or disorder must always increase. A white hole's sudden expulsion of ordered energy seems to defy this fundamental rule. Critics argue that even if white holes exist, they'd be fantastically unstable. Any stray dust particle or photon trying to enter would theoretically trigger a collapse back into a black hole. Yet proponents counter that certain quantum gravity models might stabilize them, at least temporarily. Some even speculate that fast radio bursts, those millisecond-long blasts of radio waves from deep space, could be white holes flickering in and out of existence, their brief openings releasing pent-up energy like steam from a pressure cooker. The debate gets even stranger when you consider the holographic principle. If our universe's information is stored on a two-dimensional boundary, could white holes be glitches in that cosmic hard drive, briefly spitting out data that was meant to stay erased? Or are they mathematical mirages, tricks of the equations that don't manifest in reality? Until we detect definitive proof, like a signal with the exact energy signature predicted for white hole emissions, these cosmic unicorns will remain at the fringes of astrophysics. But for theorists daring enough to explore them, white holes offer a tantalizing thought. What if the universe's most destructive objects have secret twins, somewhere out there in the void, rewriting the rules of existence one impossible signal at a time? Black holes come in two familiar sizes: stellar mass black holes, the collapsed remnants of giant stars, and supermassive ones, lurking at galaxy centers like cosmic titans. But where are the middleweights? For decades, astronomers have hunted for intermediate mass black holes. The missing link between these extremes and the signals they leave behind might finally be revealing their hiding places. Gravitational wave detectors have started picking up bizarre mergers that don't fit the usual script. Take GW190521, a collision detected in 2019 where two black holes, each around 66 times the mass of our Sun, smashed together to form something even heavier. The result, a black hole clocking in at 142 solar masses squarely in the intermediate range. This wasn't just unusual, it was unprecedented. Stellar mass black holes aren't supposed to grow this big, and supermassive ones start at hundreds of thousands of solar masses. So what created these in-between monsters? One compelling theory points to runaway mergers in dense star clusters. Picture a celestial mosh pit where black holes sink to the center, collide, and merge over and over, bulking up like cosmic bodybuilders. But even this can't fully explain the sheer mass of some detections. Another possibility: these black holes are primordial ancient relics from the Big Bang itself, born not from dying stars but from the violent density fluctuations of the early universe. If true, they've been hiding in plain sight, only revealing themselves through gravitational ripples when they finally collide. Then there's the curious case of HLX-1, an ultraluminous X-ray source in a distant galaxy. This object beams out enough energy to suggest it's powered by a black hole around 20,000 solar masses, too big to be stellar, too small to be supermassive. The kicker: it's not sitting in a galactic core where supermassive black holes usually live, but out in the galactic suburbs, like a lone wolf stalking the edges of known physics. Some researchers think it could be the stripped-down core of a dwarf galaxy devoured long ago, its black hole left behind as a cosmic trophy. But the most tantalizing clues come from star motions in globular clusters, ancient, tight-knit families of stars orbiting galaxies. In clusters like Omega Centauri and Messier 15, stars whip around their centers at speeds that suggest something massive, but invisible, is tugging on them. The math points to black holes between 1,000 and 10,000 solar masses, yet direct observations always come up empty. Are these ghosts simply too faint, or are they wrapped in cloaks of dark matter, hiding their gravitational signatures in ways we don't yet understand. The hunt is far from over. Every unexplained gravitational wave signal, every wandering X-ray beacon, and every hyperactive star cluster adds another piece to the puzzle. Intermediate mass black holes might be the universe's best-kept secret, lurking in the shadows and only whispering their presence through the faintest distortions in space-time. And if we find them, they could rewrite the story of how black holes and galaxies themselves grow from cosmic infancy to the giants we see today. Until then, their absence remains one of astronomy's quietest, most persistent mysteries. Gravity is supposed to be the ultimate cosmic straightedge, shaping light into predictable curves as it bends around massive objects like black holes. But sometimes the universe throws us a curveball. Across the cosmos, astronomers have spotted gravitational lenses that don't play by Einstein's rules, warping light in ways that make even seasoned astrophysicists double-check their equations. These aren't just subtle discrepancies, they're full-blown anomalies that hint at black holes behaving in ways we never anticipated. Take the case of galaxy cluster SDSSJ 1070 plus 5526. When scientists mapped how its gravity bent light from background galaxies, they found something bizarre, an extra kink in the lensing pattern, as if an invisible hand had reached in and tweaked space-time itself. The culprit, a rogue supermassive black hole drifting between galaxies like a cosmic wrecking ball. Unlike black holes anchored at galactic centers, this free-floating behemoth's gravity created a localized warp in the lens, a gravitational pothole that made starlight swerve unexpectedly. What's chilling is that according to models, there should be thousands of these nomads lurking in galaxy clusters, each capable of twisting light in ways that defy textbook predictions. Then there's the enigma of naked lenses, regions where light bends too much, as if magnified by something far denser than any known black hole. In 2021, the Hubble Space Telescope caught one such anomaly near quasar He 0435123. Background galaxies appeared stretched into bizarre, knotted shapes with magnification spikes that suggested a compact object with the mass of 20,000 suns, yet no visible source. The leading explanation, an intermediate mass black hole shrouded in a cloak of dark matter or debris, amplifying light like a cosmic magnifying glass with a hidden flaw. But the real head-scratchers are the lenses that flicker. Normally, gravitational lensing is as steady as a shadow, changing only over millennia. Yet in 2018, astronomers monitoring the doubly lensed quasar QSO 2237 plus 0305 saw its twin images brighten and dim in sync over mere weeks. The implication, the lensing black hole's gravity wasn't static. Something, perhaps a swarm of orbiting objects or ripples in its accretion disk, was warping space-time like a funhouse mirror in real time. These aren't just quirks, they are cracks in our understanding. Every anomalous lens forces us to ask, could black holes be lumpier than we thought, with hidden structures near their event horizons? Or is there something fundamentally off in how we model gravity's grip on light? As telescopes like Vera Rubin and Nancy Grace Roman come online, these cosmic mirages might finally reveal the truth that black holes don't just bend light. They break it. Black holes have always been thought of as the ultimate cosmic baldies, smooth, featureless, and defined only by their mass, spin, and charge. But what if they're secretly sporting a wild quantum hairdo? That's the radical idea behind the quantum hair hypothesis, a theory that could rewrite our understanding of black holes and explain some of the universe's most confounding signals. The idea starts with a puzzle. When matter vanishes into a black hole, it takes all its information with it, the type of particles, their arrangement, even the spin of every atom. Yet quantum mechanics insists this information can't truly be lost. The contradiction, known as the information paradox, has haunted physics for decades. Enter quantum hair, a proposed solution suggesting that black holes might encode information in subtle, invisible structures near their event horizons, like fine strands of cosmic hair fluttering in the quantum breeze. These wouldn't be hairs in the literal sense, but tiny deviations in the black hole's gravitational and electromagnetic fields, imprinted by the material it's consumed. Here's where it gets wild. If quantum hair exists, it could mean black holes are broadcasting their hidden complexity through the very signals we've been struggling to decode. Take gamma-ray bursts with bizarre polarization patterns, or gravitational wave echoes that don't match clean merger models. These anomalies might be the whispers of quantum hair, subtle fingerprints left by the information scrambling just beyond the event horizon. Even the mysterious repetition of some fast radio bursts could fit the picture, if their sources are black holes flickering as their quantum states reconfigure. The implications are staggering. If black holes have quantum hair, it would mean they're not the simple, voracious pits we've imagined. They'd be dynamic, textured objects, each with a unique identity shaped by everything they've ever swallowed. Signals we thought were random noise could instead be encrypted messages, chronicling a black hole's history in a language we're only beginning to decipher. Of course, not everyone's convinced. Critics argue that quantum hair would violate the no-hair theorem, a cornerstone of general relativity stating black holes should be bald. But proponents counter that quantum effects, ignored in classical physics, might weave these hairs at scales so small they've eluded detection. The debate is far from settled, but one thing's certain. If quantum hair is real, the universe's darkest objects are hiding far more beneath the surface than we ever dreamed. And the next unexplained signal we detect just might hold the comb to untangle it all. There's something unsettling about silence in a universe we expect to scream. When black holes collide, they should shake the cosmos, rippling space-time with gravitational waves that scream their violence across billions of light years. But sometimes they don't. Sometimes these cataclysmic mergers happen in perfect silence, leaving no trace in our detectors. It's as if the universe hit a cosmic mute button, and the mystery of these missing signals might rewrite everything we think we know about how black holes dance toward destruction. Take the case of GW1 90521, the first detected collision of two black holes in the elusive intermediate mass range. While LIGO and Virgo caught its final, furious moments, countless other mergers should have lit up our detectors, but didn't. Statistically, based on the density of galaxies and the lifespan of black holes, we should be swimming in gravitational wave signals. Instead, our cosmic ears are catching only whispers. The question isn't just why, it's whether these silent mergers are hiding from us, or if we're failing to listen in the right way. One possibility is that some black holes are simply born to be stealthy. Imagine a pair orbiting each other in near-perfect sync, their accretion disk stripped away by tidal forces long ago, without swirling gas to glow in X-rays or radio waves, and with spins aligned so cleanly that their merger emits gravitational waves in a direction we can't detect. These collisions might slip past unnoticed. Simulations suggest these dark binaries could be shockingly common, lurking in the voids between galaxies where dust and starlight don't betray their presence. Then there's the problem of frequency. Current detectors like LIGO are fine-tuned to catch mergers in the sweet spot between 10 and 1,000 solar masses. But what if black holes merge at extremes either so small or so colossal that their gravitational waves vibrate outside our detection range? Primordial black holes, hypothetical relics from the Big Bang with masses less than an asteroid, would merge with chirps too high-pitched for LIGO ears. On the flip side, supermassive black holes, like those at galaxy centers, merge with groans so deep and slow that their waves could take years to oscillate, far too leisurely for our current tech to recognize. But the most tantalizing and terrifying idea is that some black holes don't merge at all. Quantum mechanics suggests that at infinitesimally small scales, space-time might be foamy and chaotic. If true, black holes nearing collision could hit a quantum wall, their event horizons repelling each other like same pole magnets. Instead of merging, they'd hover just a Planck length apart, eternally trapped in a gravitational standoff. The energy of their near collision would bleed away as heat, not waves, leaving no signature except a faint evaporation of Hawking radiation, a process so achingly slow it'd be invisible to us. So are these silent mergers failures of our tools, or are black holes playing by rules we haven't discovered yet? Upcoming detectors like LISA, tuned to lower frequencies, or pulsar timing arrays that listen for waves spanning light years might finally crack the case. Until then, every missing signal is a humbling reminder. The universe's loudest explosions might be happening right under our noses, in perfect, unfathomable quiet. From the haunting whispers of the WOW signal to the rhythmic heartbeat of JRS 1915105, these 25 unexplained transmissions from black holes have one thing in common: they expose just how much we don't know. Each one is a crack in the foundation of astrophysics, a reminder that these cosmic monsters are far more than simple vacuum cleaners of the universe. They sing, they flicker, they warp reality in ways that leave even the sharpest minds scrambling for answers. Think about it, black holes shouldn't hum like Perseus's B-flat, or fling gamma rays into the void like cosmic archers. They shouldn't leave echoes in gravitational waves or hide missing matter in plain sight. And yet, here we are, staring at data that refuses to fit the models, signals that dance just beyond the edges of our understanding. The Fermi bubbles, the dark flow, the quantum hair hypothesis, these aren't just quirks. They're screaming clues that black holes are playing a game we haven't even learned the rules to. So what's next? The hunt for answers is just getting started. New telescopes, smarter algorithms, and even citizen science projects are peeling back the layers of these mysteries. But here's the thing, we can't do it alone. The universe is too big, its secrets too cleverly hidden. That's where you come in. Ever looked at the night sky and wondered about the stories it's trying to tell? Now's your chance to join the conversation. Drop a comment below. Which of these 25 signals fascinates you the most? Is it the rogue black hole bending light where it shouldn't? The overfed giants defying cosmic diet plans? Or maybe the eerie possibility that black holes are hiding entire universes inside them? And if you're hungry for more deep dives into the unknown, don't forget to subscribe. The universe isn't done surprising us, and neither are we. From dark matter to alien megastructures, there's always another mystery waiting just beyond the edge of the known. So stay curious, keep questioning, and remember, every unexplained signal, every cosmic glitch, is an invitation to look deeper. After all, the next great discovery might be hiding in the static of a radio telescope, the flicker of a gamma ray burst, or even in the comments section below. The universe is talking. Are you listening?